MacMaths, let's do some maths today. Okay, welcome back to my series of lessons on, just turning my sheet over there, sorry. As I get ready for this, I'm prepared in advance, that's me. Anyway, this series of lessons on variable acceleration, you will have watched the lesson. This is lesson 1B and it's just support for exercise 11C. So I did a short lesson from 11B, but I'm from exercise 11B going through just a couple of questions. I'm going to go through a few more with you from 11C. In fact, I think I'm going to do, there's only 6 questions, but I'm going to do the first 5 for you. Do have a go at them first though, but then if you get stuck on any of them, then you can watch these lessons, can't you? Okay, so here we go. Let's do the first one. Get my calculator here, switch that on, ready. I've left this at the side from my last little video, which I filmed about 5 minutes ago actually. S, V and A, we differentiate going down. We would integrate later on when we want to go the other way. So, a particle P, I've shortened the question, but I got them from the textbook. So this is exercise 11C, it's on page like 188 or something like that in the Pearson AS textbook. But I've abbreviated the question. A particle P moves in a straight line, distance S, displacement from a fixed point O, time T, and there you go. And you've got the equation S equals, when P is moving, so you've got to find when is P moving with a minimum velocity. Okay, so we've got S equals 0.4t cubed minus 0.3t squared minus 1.8t plus 5. Okay, if we differentiate that, we get a formula for the velocity. We need to do that first. Okay, so we times this, so we get 1.2 t squared minus 0.6t minus 1.8, and the 5 goes. Now we've got a formula for velocity. What this you can see is a quadratic equation of v in terms of t. So what would that look like? Okay, so you know it's like that, isn't it? It's a quadratic equation of v and t. Okay, and we want to find that point there. So what we actually have to do, at every point down here, the gradient of that velocity time graph is going to be the acceleration. You can see it's a variable acceleration, it's changing, it's not a straight line at the ones we've been looking at the start of the chapter. So now we need the acceleration, but it really, we want to think of it in terms of dv by dt. And we want to, because the dv by dt is the gradient of this curve, isn't it? And we want it when dv by dt is 0, is a minimum point when that gradient is 0. The acceleration in this case is 0. Okay, so 2.4t minus 0.6. Okay, and if we put that equal to 0, that's when the gradient is 0 at that point there. That is of course the minimum velocity. So 2.4t minus 0.6, and take it over to the other side. So you get 0.6 is equal to 2.4t. Divide, so you can see that t is equal to, that's a quarter, so 0.25 seconds. Okay, and it says when is p moving with a minimum velocity? Well, it's at 0, okay, so that's at 0.25 seconds. So we actually had to differentiate twice here to get down to the acceleration, but we wanted to think of the acceleration as the change in velocity in time. So you've got to think of it, as a real life graph here. The displacement of P from O at this time, so I'm not going to do that now, but if you put T, the displacement is this formula here. Oh, I did it before, so I've written that down. So if you put, for P, you just substitute T is equal to 0.25 into S equals. So you just put in 0.25 into that there, and don't forget to add your 5 on. And if you did that, you're going to get 4.54 meters. And C, and it says the velocity of P at this time. So the velocity So you stick it into there, 0.25, so substitute t is equal to 0.25 into v equals, and you get into that equation, and when you do that you actually get minus 1.88 meters per second to the minus 1, so it actually gives you a negative value. What is that telling you? Well, it's telling you that actually that minimum is down here. Okay, so it actually stops, and then it goes to you know, the minus is going in the opposite direction. Okay, so it's something that is going along and then comes back on itself. Okay, all right, so there we go. That's number one. Number two, so look at this one. A body starts from rest and moves in a straight line. It gives you the displacement, so it gives you s equals 4t cubed minus t to the power 4. You can see these equations are not like the Suvat equations at all. They're not straight, you know, they're not straight lines, are they? Well, they don't stem from the v equals u plus at. S equals 4t cubed minus t to the power 4. Show that the body returns to the start at t is equal to 4. So part A, if you put t is equal to 0 into there, you can see that s is equal to 0 as well. So it starts, you know, it starts from a particular point, and then when you put, if you put t is equal to 4 into here, you get 4 times 4 cubed minus 4 to the power of 4. You'd get s is also equal to 0. So you just have to show that by putting 4 in there, and you can see that it goes back to 0. Okay. Explain why s is always non-negative. Non-negative, I thought that means positive, so strange that it's written it that way. So explain why it is. Well, it just says explain, so you can, for all values of t between 0 and 4, not bigger than 4, but all values of t between 0 and 4, 4t cubed is going to be greater or equal to t to the power of 4 here. Okay, and if this, so you're not going to get any negative values. Okay, it's going to sort of go like that between 0 and 4. All right, so that's what you've got to explain. Find the maximum displacement of the body from the starting point. That's that point there. Okay, that's what they're asking you to find now. So that is, let's find that maximum point. So if we do ds by dt, so this is, remember, oops, let's put it there. This is the displacement over time, and we've got, we know it's a, there's more to this graph. It's actually a well, it's one that sort of, you know, it sort of goes like that. It's one of those ones actually. The t to the minus 4 is like that, and this is only part of it, part of the region of it. Anyway, we want this maximum volume, so we want the maximum volume, the maximum displacement. So that is when ds by dt is 0, isn't it? The gradient is 0. So that's going to be 12t squared minus 4t cubed. Okay, put it equal to 0. There we go. We can't, it'd be very nice, wouldn't it, to divide through by t squared, but we shouldn't do that. So we can divide through by 4 actually. So if we divide through by 4, we get 3t squared minus t cubed. And if you can't divide through by t squared, but you are allowed to factorise, so 3 minus t. So t is 0, obviously, there. And 3 minus, what makes this 0 as well, is when t is 3. Okay, and what's it saying? Find the maximum displacement. So it's the time when t is 3. So if you put t is 3 into here, so s is equal to 4 times 3 cubed minus 3 to the power of 4. Okay, and I think I worked that one out. So 2, I stuck it in when t is 3. Yeah, I got put that into your calculator, and I got 27 meters. That's what I got anyway. Okay, there we go. That was number 2. Number 3. Yeah, I didn't like this question. I'll explain why at the end. I'm not so sure they've done this right in the exercise book. Sorry, the textbook. Okay. So at t is 0, the particle leaves the origin and moves along x-axis where the velocity is t squared times 6 minus t all squared. Sketch the velocity time graph, is short than that, sorry, velocity for this motion. Now, when we did the graph sketching, new to the new A level has these, what do they, I forget what they're actually called now, but graphs where it's t to the power of, so, you know, y equals x the power of 4. And those ones, they come down, they go up, they come down and they go up like that. A bit rude, doesn't it? That's, you know, that's what they look like, these graphs. So they have these 3 sort of turning points. That's what the positive one looks like. And this is because when you square that bracket, you get a positive t squared, and times it by that, you get t to the power of 4. So it's this shape here. So for any value, so t is equal to, right, okay, so you can see here that if we want the roots of this equation for this here, if we put where is, there's velocity against time, where is the velocity 0? Well, the velocity is 0, well, t squared would have to be 0, so here, and 6 minus when this bracket is 0, so t would have to be 6, so it's 6 and 0. And because these are squared, it's a continuous point, isn't it? So it's a turning point at those. So it means it must be sort of coming down, touching down and back up like that. That's what it must be like. But because the restriction is t is greater than 0, I'm just checking this all fits on. We can't have that bit there. There we go. So that's the real life. So that's what this graph is going to look like. And you have to go back to your sketching section of the Pure book to remember that. Okay. Find the maximum value of v at the time and the time at which it occurs. This is what I don't like, because if you look at the constraint here saying for all times bigger than 0, well, the maximum the velocity is infinite, isn't it? Because it goes on up here. What it's actually referring to in the question is that point there. Okay, so what they should have really done is put a time constraint, say between 0 and 7 seconds perhaps, and then that would have been the maximum point. Okay, but actually they just said t is greater than 0, so the maximum velocity, as time goes on, the velocity increases, you know, here exponentially, so it's the velocity becomes infinitely big. But that's the point they're referring to, which you know, is not great maths, but let's find it anyway. So part B, find the maximum value. You've got to multiply all of that out. So if you multiply all of that out, you've got v is equal to t squared. That multiplied out is 36 minus 12t plus t squared, just doing it quickly. So multiplying that, you get 36t squared minus 12t cubed plus 4t to the power of 4. You can divide all of that. Oh no, you can't actually. Sorry. If we do dv by dt for this, so we want, that's our velocity time graph. Yeah, sorry. So if we we get 72t minus 36t squared. Oops. I don't know what to put a 4 there, but now I do times by that plus 4t cubed. So you can probably tell that I did this earlier and I've written it down, so I've just skipped a line while I've done it. Okay, but that is correct now. we want the minimum, so the maximum in this case, so in other words when the gradient is 0, so we put that equal to 0. There we go. We can divide all of that by 4 now throughout because it's equal to 0, so 0 divided by 4 is 0. And I'm just going to switch it around actually because that'll make it nicer. So divide that by 4 and we get t cubed. Then we can put this in the middle, halve it and halve it again, 18, 9, t squared, and divide that by, so that's 36, 18, isn't it? So we get that, and then we're going to factorise it. And luckily we can take out t because it's t, so we get t squared minus 9t plus 18, and then this is going to go into 2 brackets, isn't it? T and t, and it's minus 3 and minus 6. Okay, so you can see here that we knew that was coming. There's our root. T is equal to 0. We get t is equal to 0, t is equal to 3, and t is equal to 6. Those are the 3 turning points. There's the turning point there that we had. That's that turning point. T is equal to 3. That's the one that they want in the question, and t is equal to 6 here. Okay, which we had. That's a minimum point and a minimum point at 0. So that's the one that we want. And if you substitute t is 3 into this equation here, to the power of 4, okay, you get the velocity is equal to 81 meters per second to the minus 1. Okay, and that's that one. That's number 3. So that's that at 81 there. Let's put that in. Okay, hope that was okay for you. I had to teach myself these graphs now because I haven't done those since I was at school. They've not been on the A level for a long time, the standard A level. Not while I've been teaching it, the 25 years I've been teaching it, but when I was at school they were. Number 4. Okay, let's have a look at number 4. So a particle v is equal to, so you've got a velocity time. Okay, and you can see it's a quadratic, so just think, always have a thought about what that looks like. T and v is a quadratic equation, isn't it? Okay, show that it never comes to rest. Right, okay, if you're showing that it never comes to rest, so that means that the velocity does not get down to 0. So in other words, it must be up here. So I've done it right the first time without thinking about it. It can't be, what it can't be is that, because at that point there the velocity is 0. In other words, it comes to rest and then starts going in the opposite direction to be a negative velocity. Okay, so how do we show that? Well, this equation, of course, going back to our knowledge of maths and quadratics, it does not have any roots. And if it doesn't have any roots, then the discriminant, remember, b squared minus 4ac is less than 0, isn't it? Okay, the discriminant is less than 0. And that means that when you use the quadratic formula, the discriminant is the bit under the square root. And if that is less than 0, that is negative. And if it's negative and you try and square root negative, you get an error on your calculator, don't you? So you can't work any roots out. So that's what we're looking for. So you just have to show that the discriminant of this. So your b squared is 9, minus 3 squared is 9, minus 4ac, 4 times 2, times 5, so you've got 9 minus 4/8, minus 40. Okay, so 9 minus 40 is negative, and therefore it never comes to rest. There's no velocity. 0. Find the minimum velocity. So let's find this point then. Okay, so what do? We go dv by dt is 4t minus 3, and then we put that equal to 0. The gradient of that, this is the gradient of this curve. It's actually an acceleration as well, isn't it? but it's when that is 0. So you've got 4t minus 3 is equal to 0, so 3 is equal to 4t, t is equal to 3/4, so 0.75 seconds. But the question is saying the minimum velocity, so it wants the velocity, and you substitute that back into there. And I have done that, I think. Yeah, and I got a velocity. If you put it back into there, you get a velocity of 3.875 meters per second to the minus 1. I think they've rounded it off to a couple of decimal places in the back of the book. Okay, so substitute that back in, and you get a velocity of 3.875. So it slows down to that and then starts speeding up again. Okay, and I'll do number 5 for you. It says number 5. There seems to be a lot of marks for question 5. It says question 5 is an exact problem, but also an exam question as well. So we've got s equals 9 over 2 t squared minus t cubed. Okay, now this is, it gives the constraint of between time for this model is only between 0 and 4.5 seconds. First thing I did, you can see that putting 0 into there gives you s is 0, but the first thing I did is put 4.5 into there as well. Okay, and when you put 4.5 into there, because what I expected happened, and that was s is 0. So this is describing something that's going away. The displacement is going away from the origin and then coming back after 4.5 seconds. It's a cubic function, and it's a negative cubic function, so it's going like that, isn't it? That's what it's going like. And you know, it's at 0 and at 4.5. There we go. So that's what it's going to be like, the displacement s against time. There it is. And the displacement at, oh, hang on, what are you talking about? S and t, idiot. That's me, that, sorry, not you lot. So the displacement is 0 at the start, at t is equal to 0, and it is at 4.5 seconds, it's 0 as well. So that's it. And of course this doesn't exist, and that doesn't exist because the constraint is only between 0 and 4.5. So rub out your tail, think about it as a cubic, but then rub out your bits. You don't want to show those on the exam. And then part B, we've sketched it, and part B hence justify the restriction. So it's saying that the restriction is really sort of saying that the displacement is always positive, is in one direction, it's never negative. It's, I don't know if it's something travelling up from the ground and coming back again, okay, but it never goes the other way. Find the maximum distance from O. So this is displacement, so it's that maximum there, okay, and the gradient of that maximum is 0. So what are we doing? We are differentiating this, aren't we? ds by dt. Of course that is the velocity, but so that becomes 9t minus 3t squared. Put it equal to 0. 9t minus 3t squared. And if we factorise that, oh, we can divide by 3, can't we? So 0 is equal to 3t minus t squared. And if we factorise 3 minus t, there you go. You can see it's at t is 0. And that's a turning point there that we knew, that we'd sort of worked out, and t is equal to 3 there. 3. So at t is equal to 3, but what's it saying? Find the maximum distance. So you've got to put 3 back into there. Now I did that. So s is equal to 9 over 2 times 3 squared minus 3 cubed. And when you do that, you get 13.5 metres. Now the next bit is interesting. It says find the magnitude of the acceleration at this point. Okay, so that's the velocity. This is what we've got here. It's making sure that you understand that's the velocity, but you've got to go down another level to get the acceleration. So, and this is interesting. So now you've got the velocity is 9t minus 3t squared. dv by dt is the acceleration, and that gives you 9 minus 6t. Okay, and we know that you know, the time we've already worked out what that is. The time is at 3. So what is the acceleration at this time? Well, it's 9 minus 18. So the acceleration is minus 9 meters per second to the minus 2. Now what that is saying, in the back of the book, the answer is 9 meters per second squared. That's the acceleration. It's actually, and it just puts it in like that, it's actually a deceleration. At that point it's actually slowing down, so I prefer to write it down as minus 9, or to make a point of saying it's 9 meters per second squared, yes, but it's a deceleration, not an acceleration. Okay, because that's what that minus means. Our number 6 didn't even look at question 6 as one. Well, you can do that. I've done the first 5 for you, and they've highlighted this one as the exam question. Okay, I hope that helped you, and I hope you had a go at them first, and you're getting used to thinking about things, you know, graphically, but also, you know, with one foot in the real world.